Hi, I'm Frank O'Brien, and welcome to our talk on studying the nearest star, our Sun. Before we start, once again, I'm hoping that you, your family, and all of your friends have been safe and healthy during this pandemic. That's really the most important thing right now. Now, when we think of astronomy, we generally assume that we're talking about stars that are light years, hundreds of thousands of light years away. This makes observations of them especially tough. But we do have a star that's pretty close to us. And this makes it a whole lot easier. That star, of course, is our own Sun. So much of what we know about these powerhouses of light and heat have come from these observations of our own Sun. And we can take that knowledge and extend it to the other stars in the galaxy and even those throughout the entire universe. Now, just a few quick words about me. I've been one of the editors of the NASA website that extensively documents the Apollo moon landings. And about a decade ago, I was accepted as a NASA Solar System Ambassador. There's about 1,000 of us all across the U.S. who go into communities and share insights on the NASA mission. I've talked all over at schools and libraries, museums, and computer conferences. We're often the first opportunity for those in the community to interact with someone who has direct connections to NASA. This is a fantastic, all-volunteer program. No tax dollars are spent on it, and of course, we never accept any kind of compensation. Now, basic information about the Sun usually involves numbers that are so incredibly large they go well beyond any kind of human comprehension. And that's okay. The basic gee whiz kind of numbers start with its size. It's about 865,000 miles across. With that kind of size, it's also massive, about 330,000 times that of Earth. And it accounts for 99.9, just about all the mass in the entire solar system. The Sun is simply an incredibly hot ball of gas, and not a rigid body like the Earth. Because of this, it can spin faster at the equator in about 25 days to complete a revolution, but it takes 35 days in areas by the poles to completely go around. The vast majority of its mass is in the form of hydrogen, about 71%, with another 27% taken up by helium. But dozens of other elements are already included. We have carbon, we have oxygen, nitrogen, and perhaps surprisingly, about 0.14% of the Sun is iron. Every 11 years, the number of sunspots rises and falls, which reflect the activity level on the Sun's surface. A new solar cycle started at the end of 2019, and right now, in April of 2021, we're coming out of the last solar minimum. We're expecting solar activity to peak around mid-2025. A surprising thing happens during these solar cycles. During each 11-year cycle, the magnetic poles completely flip. Yes, the North Pole becomes a South Pole and vice versa. And over 22 years, each pole undergoes a complete flip. The surface of the Sun is an incredible 10,000 degrees, but it turns out that's the coolest part. In the core, its temperature is about 27 million degrees. Now, we're going to be talking about two complementary topics. The Sun itself, which is a full topic all by itself, but a separate and completely interconnected topic is the heliosphere, which is that region of gas particles and magnetic fields that come from the Sun itself. Each presents examples of extreme physics, and the understanding of their interaction with the Earth is essential for understanding its impact on modern society. In the core of the sun, the dominant energy source is the fusion of hydrogen into helium. 4 hydrogen atoms fuse together to create a single helium atom. Now, since the mass of 4 hydrogens is more than a single helium, the extra mass is converted directly into energy from that classic equation from Einstein, E equals mc squared. This is a process that is staggeringly difficult to do here on Earth, at least in a controlled fashion. The temperatures, tens of millions of degrees, and pressures that are estimated at maybe 1 trillion psi are necessary to sustain this reaction. There is one example where we do know how to do this kind of fusion, and that's in a thermonuclear bomb. And as you can imagine, we're probably not likely going to see nuclear bombs used as power sources on Earth anytime soon. With all that energy being generated in the core of the sun, it eventually makes its way to the surface where we see all the plasma being expelled from the sun. Now, this isn't a uniform process. Turbulence within the inner layers, convection, and huge magnetic fields cause the effects we see on the surface. These are terribly complex processes, and honestly, they're not quite understood very well by scientists. Now, when the particles from the interior of the sun reach the surface, they fly off into space into a region called the heliosphere. We feel this locally on the Earth and simply call it the solar wind. It extends billions of miles from the sun until it meets the interstellar medium, the flowing region of dust and gas that's part of the Milky Way. The Voyager spacecrafts, launched over 40 years ago, have recently reached the end of the heliosphere and have now entered interstellar space. Unfortunately, the study of the heliosphere, which is full of particles and magnetic fields, doesn't lend itself to many pretty pictures, unfortunately. Now, while the heliosphere as a whole is a great topic for another talk, let's focus specifically on that part of the heliosphere within our local solar system, namely the corona. Now, the corona can be thought as the inner part of the heliosphere, extending out a few 100 million miles, easily past the orbit of Mars. This is the flow of, again, particles and gas from the sun, traveling several million miles an hour, and one thing has baffled scientists for over 150 years. Here's the problem. The surface of the sun is about 10,000 degrees. That's really pretty hot. But a little bit above the surface, the temperature of all that material being ejected reaches 10 million and higher degrees. This absolutely makes no sense at all. It's as if you're walking further and further away from a campfire and it's getting hotter and hotter and hotter. This makes no sense at all, as it appears it would violate every known law of physics. We'll talk a little bit about some of the possible answers we've come up with a little bit later on in the talk. Now, understanding these particles is not just an academic exercise. They directly impact the Earth, and more importantly, the satellites and humans we've put into space. While the Earth's magnetic field does protect us from the majority of these energetic particles radiating from the sun, it's not perfect. In particular, there's weak regions by the north and south magnetic poles, which effectively act as funnels for the charged particles, directing them down towards rather than away from the Earth. So, What's the result of highly energetic particles hitting the atmosphere? Well, the oxygen, which is higher up in the atmosphere, and the nitrogen below it, light up exactly the same way a neon tube illuminates, and you get an aurora. These are magnificent displays in the atmosphere, but you have to live quite north to be able to see them. Here in New Jersey, it's really simply too far south. However, Alaska, Iceland, countries in Scandinavia are all famous for having aurora watches where you can get onto a tour and watch the auroras. The sight simply isn't something you should miss if you can. Now, if you haven't seen an aurora, a single picture won't do it justice. Here's a short clip of the ISS flying over auroras at night. Notice how the auroras swirl and flow as the Earth's magnetic field is being disrupted by the incoming particles. Wow, that's an incredible sight, and hopefully in your travels you'll get the opportunity to see it sometime. We in the beginnings of the space age began to get an understanding of what we call space weather. And like the more traditional weather on Earth, with its forecasts of temperature ranges plus rain or snow or whatever, NOAA also publishes its daily space weather forecasts. And as we'll see in a bit, these are essential to the people who operate the electrical grid and satellites as well. They also publish a daily aurora forecast. Because the sun is in its quiet phase of its 11-year cycle, the diagram only shows a small probability of auroras in the northern hemisphere. Now, how do we go about studying the sun? Well, unlike so many other objects in the sky, the sun is certainly bright enough and big enough to see. Many solar telescopes have been built around the world, most notably the Inouye telescope in Hawaii, which just opened up last year. In this telescope, the 4-meter mirror and advanced optics allow previously unavailable high-resolution images of the sun's surface to be observed. And as you can see, the Inouye telescope doesn't really look like a traditional telescope. This is because advancements in optics and the requirements for a solar telescope make its design very different from the familiar tubes you see in traditional telescopes. As a treat, we'll see the view from the telescope next. With such telescopes, we can study those convective currents on the surface and can even infer the magnetic fields as they interact with the plasma. The view from the new solar telescope is like nothing ever seen before. We see the convective bubbles of plasma coming up in near real time and in unprecedented detail. Now, the most interesting wavelengths to study the sun are in the extreme ultraviolet. But as you can see from our little chart here, the atmosphere absorbs practically all of these wavelengths. The region to the left shows the absorption of UV light and is primarily the result of the oxygen, ozone, and water vapor in the atmosphere. At the same time, the atmosphere also blocks X-rays and gamma rays that come from the sun. This is not a bad thing, as the extremely high energy photons from the sun are so intense that life on Earth, if it survived at all, would look very different than it does today. Now, before we talk about observing the sun, one point has to be made clear. Please never look at the sun with your bare eyes. Remember, this is how Galileo went blind, and so will you. When we look at the sun through, of course, a very dark filter, we generally see pretty much a featureless disk. Oh, the sunspots will stand out, but the rest of the image is, well, it's pretty underwhelming. The solution is to use special filters that highlight particular activity on the sun. Importantly, the choice of filters is very specific. You want to use those that are centered on a particular ionization level of an element. For example, by using a special filter centered on the hydrogen alpha line, which is about 656 nanometers, you're observing the change in hydrogen from one ionization level to another. When hydrogen makes that transition, it sends out a very precise light that can be easily observed. The part of the sun that you're able to see is called the chromosphere and is indicated that it has a temperature between 11,000 and 36,000 degrees. Astronomers on the ground like to use this wavelength because it's very bright and the equipment is relatively affordable. Now, just our little hydrogen alpha observations cracked open the door to one of the big mysteries of the sun. With a surface temperature of 10,000 degrees, how is it that we're observing structures up to 36,000 degrees Fahrenheit? Even amateurs are able to recognize this oddity. Unfortunately, to see higher temperatures and the structures that compose them, we need to look into far, far smaller wavelengths, again, specifically in the extreme ultraviolet. Additionally, we need to identify those elements which send out spectral lines at those impossibly high temperatures. And, of course, they have to exist on the sun. As we learned earlier, the atmosphere blocks those wavelengths from reaching the surface of the Earth. So, we have no choice but to get above the atmosphere and study the sun and its heliosphere from space. One spacecraft in particular, the Solar Dynamics Observatory, or SDO as we call it, takes advantage of the physics of very hot objects to see the sun. These are some of the images that SDO takes of the sun once every few minutes. For example, when we're looking at the 4500 angstrom filter, we see the sun pretty much as we would on Earth. And here it's colored yellow. Colors in these images are completely arbitrary, but they're all standardized for easy reference. As we move further across and down the table, we're seeing higher and higher temperatures. In the image of gold, we use a filter that's centered on the iron 9 spectral line. That is iron which has lost 9 of its electrons. And this occurs at a temperature of about 1 million degrees. At these temperatures, we're able to see structures called coronal loops, which show the magnetic activity on the surface. Next to it, in brown, are structures seen when iron is ionized to lose 12 of its electrons and reflects a temperature of about 2 million degrees. Finally, at the end, in green and teal, are the areas between 10 and 20 million degrees. And we use these as the best source of imagery to observe flares from the sun. So from these series of pictures, we're able to watch the dynamics of the sun in many different levels. A fleet of satellites, past, current, and planned, are dedicated to studying the sun. But why so many and such a variety? Well, it's tough to observe the sun at night, so a single telescope isn't going to work. Okay, that's a joke. But it's true that to make comprehensive observations, the sun needs to be observed continuously. Many of the most interesting and important events are the ones that happen and occur over very short time frames. Even the largest flares erupt and appear to dissipate in just a matter of minutes. Particles being released from the sun are easily blocked by the magnetic field and atmosphere, so it's only possible to measure their composition and energy as they're flying by. The complex magnetic fields that are also part of the heliosphere must also be measured away from the Earth before they get completely intertwined with the Earth's magnetic field. Given the complexity of the sun, the heliosphere, and its interaction with Earth, many of these satellites are tasked with very specific science objectives. It's simply not possible to have one satellite with one set of instruments to try answering the entire puzzle. It really is just too complex. Unfortunately, many of the satellites in this picture are quite old. A very important one called SOHO is over 25 years old and nearing the end of its life. A few are new, such as the Parker Solar Probe and the European Solar Orbiter, and we'll be talking about a few of the notable spacecraft in a bit. So, why is studying the sun, with all of its complexity, so important? After all, the sun rises in the morning, seems to be pretty steady, and sets at night only to return tomorrow. We're pretty good at figuring that out. How much more do we need to know? Well, it turns out the sun is anything but benign. It would be tough to believe that a controlled thermonuclear bomb would be anything else. We mentioned before that the sun follows approximately an 11-year cycle between its minimum and maximum and back to its minimum levels of activity. We're not certain why this happens, but we do see that it happens quite regularly. This is a plot of the last 35 years ending in 2020. Going into the year 2021, we're starting at a point where the solar activity is at a minimum. Yes, it's a bit of an old chart, but the solar forecast for the cycle we're in right now, called Solar Cycle 25, is that it's going to hopefully be a mild one. And trust me, that's a good thing. Now, do you notice the spike around 1989 over here on the left? Yeah, we're going to be talking a little bit about that. Folks have been observing the sun for decades, hoping to divine some understanding of what they've been seeing and try to correlate it with the weather or the success of this year's harvest. Well, spoiler alert, the sun doesn't have a lot to do with either of these. But astronomers, both professional and amateur, were making constant observations even as far back as the middle of the 19th century. In England, Richard Carrington, on September 1st, 1859, was observing a large group of sunspots when a massive group of flares erupted. These lasted nearly 15 minutes, far, far longer than the typical flare's lifetime. While the light from the flare was instantly visible, what wasn't seen, or known at the time, is that a massive, massive cloud of hot, energetic particles and magnetic field were heading towards the Earth. The output of the flare reached the Earth in a little over 17 hours, far faster than the several days that it usually takes for a flare to make the 93 million mile journey. On hitting the Earth, several dramatic effects occurred. The disruption of the Earth's magnetic field induced a current in the ground. Now, the only widespread application of electricity that was used at the time was the telegraph, which depended on a known and fixed value of the ground potential. Now, with the current flowing in essentially the opposite direction, telegraph lines became highly charged, and the operators were shocked, literally, by sparks flowing out of their equipment. Not completely understanding what was happening, many telegraph offices were asked to disconnect their batteries from the circuits. The end result was that not only did the telegraphs continue to work, they worked apparently better than they were before the event. Auroras, which are rarely seen in the continental United States, not only lit up the lower 48, but were easily visible as far south as Cuba. Apparently, the skies were so bright in New York, it was not difficult to read a newspaper in the middle of the night by the light of the aurora. The event of 1859, which is now referred to as the Carrington event, might be thought of as a once-in-a-lifetime, or hopefully even longer, event. And if that was true, that would be great. But in reality, they occur with far greater frequency and usually follow the 11-year solar cycle. In May 1921, a huge solar storm hit and wiped out the power for railroads in the New York City area. Telegraphs literally burst into flames, and operators were shocked with nearly 2,000 volts of electricity. Like the Carrington event, the only positive note was that society had not become fully dependent on electricity and elaborate communications. Well, in March 1989, all of that changed. Another massive storm hit the Canadian provinces in the early morning hours. Within 90 seconds, currents induced in the transmission lines completely overwhelmed the grid in Quebec. Power stations were knocked offline, and significant damage occurred within the transmission system. The image here is that of the size and intensity of the storm over just 3 minutes, and is one of the very first space-based measurements of a storm of this magnitude. For 9 hours, millions of consumers were without power. As a result of these events, regulators in the United States and around the world have created requirements to strengthen the resilience of power grids to solar storms. With all of the science to be learned and all of the hazards that we need to be alerted to, a flotilla of spacecraft are employed. As we mentioned, the environment is so complex it just isn't practical to load up one spacecraft with all different instruments to help solve all of these mysteries. As a result, each satellite has a specific task to perform, although there is a fair amount of overlap between them. One of the earliest, called the Solar and Heliophysics Observatory, was launched in 1995, and again, it's certainly near the end of its life. It provides vivid images of the flares and coronal mass ejections of the sun. It's located about 1 million miles from Earth at a location which has an uninterrupted view of the sun. To see the value of the images it returns, let's take a look back at the solar storm of Halloween 2003, which was a particularly intense event. You'll see the flares and ejections of matter over the few days before the event. And then finally, there are several events where the hot and energetic material hits the spacecraft directly on its way to the Earth and reduces the images to little more than just static. One of the more productive spacecraft is the Solar Dynamics Observatory, which was launched in 2010. It observes the sun in several different wavelengths and gives timely data on the state of the sun. Unlike SOHO, it doesn't give that wide field view of the sun, but focuses in on the finer structures of the sun and corona. Other instruments map the movement of material on the surface and the magnetic fields. The earlier slide that we saw showing the different images of the sun were all taken by the Solar Dynamics Observatory. When you look at a video clip of images taken from SDO, you can see the improvement in resolution over SOHO. As we've seen, observing space weather is a critical need for our technological society. So, it might not be a surprise to learn that the latest series of weather satellites, called GOES, are also equipped with instruments to study the sun. Telescopes, similar to what's found on the Solar Dynamics Observatory, observe the sun in multiple wavelengths, and other instruments record energetic particles and fields that are hitting the Earth. While the primary mission of GOES is to study the Earth's weather, it's an important complement to dedicated satellites like SOHO and SDO. If either of those satellites fail unexpectedly, the GOES satellites can provide data, although at much lower resolution. The flagship spacecraft dedicated to studying the sun is the Parker Solar Probe. Intended to study the sun at an altitude of only a few million miles above its surface, it travels deep within the corona to observe this mysterious process directly. Considered a priority of science for nearly 50 years, it was only recently possible to design a spacecraft that could endure the temperatures that could easily reach hundreds of thousands of degrees. A unique carbon fiber heat shield protects the rest of the spacecraft, and you can see it's painted white and placed at the top of the spacecraft. During the close approaches to the sun, the heat shield heats up to about 2,500 degrees. Remarkably, in the shadow of the heat shield, the rest of the spacecraft is only a little warmer than room temperature. Now, although there's a camera on board, its mission really isn't designed to return pretty pictures. Its mission is to study in detail the various particles streaming out from the sun, and as importantly, the wildly changing magnetic fields. From the data that has been returned from Parker already, we think we're starting to understand the mystery of the coronal heating. The Parker Solar Probe isn't a particularly large spacecraft, and it weighs in at only about 1,500 pounds. Yet to achieve an orbit so close to the sun, it must be traveling very, very, very fast. The largest rocket available, the Delta IV Heavy, was used to launch Parker, yet it still needed a special upper stage to accelerate it even further. Still, that wasn't nearly enough. To achieve the 430,000 miles an hour speed needed for a close approach to the sun, Parker flies an incredibly complex trajectory, using gravity assist from Venus that will occur over 7 different occasions. Each time it passes Venus, Parker accelerates by exchanging momentum with Venus, which slows down a little bit as Parker speeds up. Next week, Parker will be making its 7th close approach to the sun before it flies out for millions of miles to cool down and transmit its data. Finally, Parker has given us insights as to why the corona heats up as it travels away from the sun. First, in a scale far smaller than the overall sun, magnetic fields are chaotic and they're all over the place. And they aren't like that smooth field that you would see visualized around a bar magnet. Next, the magnetic fields are tied to the charged particles ejecting from the sun. Since the sun doesn't eject these particles uniformly, there's a vast difference in speeds as they travel away. Faster blobs of particles overtake the slower ones, forcing the local magnetic fields into this switchback configuration as you see in the diagram. What happens next is incredibly complex, but reasonably well understood. As the magnetic fields collide, a phenomenon known as reconnection occurs, where the fields interact with each other. Magnetic reconnection releases huge amounts of energy, and that's imparted back onto the particles. Now, we believe that this is the likely source of heating in the corona. Of course, Parker will continue to study this effect, and scientists are looking forward to refining their understanding. So, that's our talk on studying the nearest star, the sun. I hope you will join us next month on May 30th, where we're going to be having a new lecture on discovering exoplanets, those worlds orbiting stars other than our sun. What we have found will amaze you. Until then, thank you again, and please stay well.